Imagine for a moment if everything around you, from the smallest atom to the vast cosmos, is nothing more than a sophisticated simulation. Yes, we're diving straight into the simulation theory today. The concept of the simulation hypothesis is as intriguing as it is mind-boggling. What if the universe we know, with its infinite galaxies and innumerable stars, is nothing more than a computer program run by an advanced civilization? The idea might sound like it's straight out of a science fiction novel, but it's a concept that has piqued the interest of renowned physicists like Neil deGrasse Tyson. The famous astrophysicist has even suggested that there's a 50-50 chance our entire existence is a program on someone else's hard drive. But the origin of this theory traces back to Oxford philosopher Nick Bostrom. In 2003, he proposed that future generations might have computers so powerful they could run detailed simulations of their forebears. In such a scenario, we could be those simulated ancestors oblivious to our true reality. And it's not just academics who are fascinated by this hypothesis. Elon Musk, the visionary CEO of SpaceX, has made headlines with his take on the simulation theory. Musk believes that there's a 1 in billions chance that we're living in base reality, or what we understand as the real world. The idea is that if a civilization could reach a post-human stage and possesses immense computational power, it could run numerous simulations, creating a multiverse of simulated realities. In such a case, the odds of us living in the one true reality would be astronomically low. But what kind of evidence could support such a radical theory? Well, as you can imagine, proving we live in a simulation is no easy task. However, there are intriguing hints in the realms of quantum physics and cosmology that suggest our reality might not be as real as we think. With such a mind-bending concept, it's time we delve into the numbers and data that could support this theory. If we were in a simulation, the computational power needed to run such a simulation would be astronomical. Let's explore this further. Visualize for a moment the complexity of a single human being. There are approximately 70 octillion atoms in the human body. That's a 70 followed by 27 zeros. Now think about the fact that there are nearly 8 billion humans on Earth. The sheer number of atoms in all humans combined would be a figure so large it's almost beyond comprehension. But let's not stop there. If we're considering the possibility of a fully simulated universe, we need to account for more than just humans. We need to consider every single atom in the universe. Current estimates place this number around 10 duodecillion. That's a 1 followed by 80 zeros, so if each atom were to be simulated, the computational power required would be colossal. Each atom would need to be accurately tracked and rendered in real time, accounting for its position, velocity, and interactions with other atoms. Now let's consider the processing speed required for such a simulation. Even the world's most powerful supercomputer, as of our current technology, would be woefully inadequate for this task. We're not just talking about a few orders of magnitude here. We're talking about a computational demand that is so far beyond our current capabilities. It's almost like comparing a single grain of sand to the entire Sahara Desert. Moreover, this doesn't even take into consideration the storage capacity required to hold all the information about every atom, its state, and its history. The numbers are almost inconceivable. In essence, simulating a universe down to the atomic level would require a level of computational power that is currently beyond our grasp. It's an interesting concept to ponder, isn't it? The sheer scale of the numbers involved is enough to make your head spin. The numbers are staggering, aren't they? These figures give us a glimpse of the immense computational power required. The strange world of quantum mechanics might just provide some evidence for the simulation theory. Now let's dive into the deep end of the pool of quantum weirdness. One of the most emblematic experiments in quantum physics is the double-slit experiment. When we fire particles like electrons or photons at two slits, they behave both as particles and waves, creating an interference pattern. But here's the kicker. Even when we fire these particles one at a time, they still form the same pattern. It's as if they know about the other potential paths they could have taken. It's like a video game character that can simultaneously take multiple routes to reach the same destination. Could this be a computational shortcut of the simulation we're in? Next, let's talk about quantum entanglement, a phenomenon so bizarre that Einstein himself called it spooky action at a distance. When two particles become entangled, their states become linked, no matter how far apart they are. If we change the state of one, the other instantaneously reflects that change. It's as if they're cheating the speed of light, communicating across vast distances in the blink of an eye. Again, it's almost like a cheat code in our hypothetical simulation, bypassing the usual rules of the game. Lastly, we have the observer effect. In quantum mechanics, the act of observation changes the state of what's being observed. An electron exists in a cloud of probabilities until we measure it, at which point it snaps into a definite position. It's as if the simulation doesn't bother rendering the details until someone is looking. Much like how a video game only loads the graphics that are visible to the player to save computing power. These quantum phenomena could be seen as glitches or shortcuts in the simulation, much like how a video game might handle complex calculations. It's a fascinating perspective that offers a new way to think about these strange quantum behaviors. Quantum mechanics, with its peculiarities, does give some food for thought on the simulation theory. The Fermi paradox, the apparent contradiction between the lack of evidence for extraterrestrial life and various estimates for their probability, could also tie into the simulation theory. The Fermi paradox is a fascinating conundrum that challenges our understanding of the universe. Named after physicist Enrico Fermi, the paradox grapples with the apparent contradiction between the high probability of extraterrestrial life and the stark lack of evidence or contact with such civilizations. To understand this paradox, we need to delve into the Drake equation. This equation, developed by astrophysicist Frank Drake, is not designed to quantify the number of civilizations, but to stimulate scientific dialogue. It combines the rate of star formation, the fraction of those stars with planetary systems, the number of planets that could potentially support life, the fraction of planets where life could evolve, the proportion of life forms that could develop a technology that releases detectable signs of their existence into space, and the length of time such civilizations release detectable signals. When we plug in even conservative estimates into the Drake equation, we arrive at a significant number of civilizations within our galaxy alone, yet we have no evidence of them, a silence that is deafening. This is the crux of the Fermi paradox. Now let's connect this paradox with the simulation theory. What if the reason we haven't found evidence of other civilizations is that we are living in a simulation? Could it be that our creators have decided to simulate only our planet and our species, or perhaps they have programmed us to be incapable of detecting other simulated civilizations? This idea might seem far-fetched, but it is a possibility that cannot be dismissed out of hand. In a simulated universe, the rules are determined by the creators of the simulation. They could control what we can and cannot perceive and shape our understanding of the universe around us. Could the silence of the cosmos be another clue pointing towards our reality being a simulation? It's a question that challenges our perception of reality and pushes the boundaries of our scientific and philosophical understanding. So, what if the simulation theory were true and we were living in a simulation? Let's take a moment to recap. We've delved into the staggering computational power required to simulate an entire universe, which in its own right is mind-boggling. We've also explored the strange and wonderful world of quantum mechanics, where particles can be in two places at once, and reality doesn't solidify until observed. And we've pondered the Fermi paradox, the seeming contradiction between the high probability of extraterrestrial life and the lack of contact or evidence. If the simulation theory were true, it could imply the existence of multiple simulations or parallel universes, each with its own set of physical laws. The implications are both fascinating and terrifying, pushing the boundaries of what we consider to be reality.